Okay, so today I want to start by wrapping up some loose ends. And the first thing is idempotent completion. Of a category. So I guess I'll call the category C. So we say C is idempotent complete. If for every idempotent A, so we have the following diagram. So here's A, here's E, so this is for every one of these things. There exists a map, an object, which I'll call EA, and a morphism from A to EA, and a morphism back, such that if I do this twice, I get the identity. So this is just a fancy way of saying that if you have an idempotent, it splits as a projection onto some factor followed by the inclusion of that factor. And this makes sense for any category. And there's a universal map to an idempotent complete category. And roughly speaking, what you do is you make the objects are pairs consisting of an object A and an idempotent E. And then the morphisms are just morphism. A morphism from AE to A prime E prime would be a morphism from A to A prime, which is compatible with this idempotent. So this always exists. And the standard example that everybody uses is if C is equal to free R modules, and then so let's see, I'm going to want a name for this idempotent completion, so we'll call this C goes to C hat. So if C is a category of free modules, then C hat is equal to projective modules. So you just take summands of, so one way of doing this is to embed yourself in a much larger category, which is idempotent complete, and then just take all of the objects in that larger category, which are summands of the objects in the original category. Now the point of this is that if you have something like this, so if C is Waldhausen, so that this makes sense. So there's a fibration sequence. Whoops. I said this backwards. Let's define gamma to be the co-kernel of this map. And then the point is that Kn of C is equal to Kn of C prime for all n greater than or equal to 1. Clearly they're not, well, let's see. So then,
prime is het.
Oh, that is a, yes. K0 of C is actually a subgroup of K0 of C prime, C hat. And so the only difference between the higher K theory of these two is just the difference in K0. But if n is negative, Kn of C is not defined. So the only way we know how to define negative K groups is for negative K groups of idempotent complete things. And so the trick that we did last time in the de-looping so we embedded A into something called the cone of A, and then we formed the quotient So, well, this is what the suspension of A was supposed to have been. And I don't remember if I actually said that or not, but the point is that you have to idempotent complete after every single stage. And if you don't take the idempotent completions into account, you just get the wrong stuff. So the typical way that you do this is you take Kn of A, K minus 1 of A is defined to be K0 of the cone of A over A hat, and etc. So the rest of the game that I was telling you about basically depends on one iteration, and this is the iteration, and there's a completion that has to happen in there. And when you see a lot of exposition about this, the idempotent completion gets kind of buried in the story, but I want to bring it out because it actually makes a big difference. So this happens, for example, if X is the union of U and V, so this is of some variety. And so then what we have is, say, the K-theory of X. Let me draw a picture. Here's U. Here's V. This is V. And this shaded thing is the complement, so that's Z. So Z is X minus U. So what I showed you last time is that we had a sequence that goes like this. But also you notice that Z is the complement of this intersection in here. And so we also get a sequence which is the K of V on V intersect Z. And this goes to the K-theory of V. And this goes to the K-theory of U intersect V. And of course there are maps. And now the miracle happens, and that is the following thing. The key lemma that we had before the key lemma said basically that if you had an object in the a chain complex, well, let's see, how do I say this? If you have a chain complex representing an object here, and its class in K0 vanished in this group gamma, then it came from the previous, then it came from a chain complex of vector bundles here. So that applies to V and U intersect V as well. And so if you have a chain complex on U intersect V, and it comes from, the class in K0 comes from something here, then in fact it actually does come from something here up to quasi-isomorphism, and that allows you to make this diagram. But the point of that is that that says basically if I have something here, it comes from something there, and that becomes a homotopy equivalence. The point of that being homotopy equivalence is that makes this homotopy Cartesian. Because to say that a square is homotopy Cartesian, one way of saying it, is to say that if you take the horizontal fibers, that they're homotopy equivalent. So what this means is you get a long exact sequence of the Meyer-Vietoris type. Well, I will imagine that you know how to spell Meyer-Vietoris. So you have the K-theory of U intersect V goes by the boundary map to the K-theory of X, goes to the K-theory of U plus the K-theory of V, goes to the K-theory of U intersect V, and then there's a boundary map and so on. And this works for all integers now, because what we've done is we've sort of done enough idempotent completions all along the way when we were defining negative K groups that this extends from positive to negative K groups. So this is what we call open excision. And that is that if you have a covering by opens, then this is excision. Okay. So that was the first thing I wanted to get out of the way. I didn't say this, but when I wrote K0, K0 here, but if I did K of C to K of C hat to gamma, this is actually a vibration sequence of spectra. So gamma is an Eilenberg-MacLane spectrum. It's just something which has homotopy groups in pi 0 and nothing in any other homotopy group. And what we've done is we've just artificially jimmied this so that K0, 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 I mean pi 0, pi 0, pi 0 to 0 is okay. And since this is a connective spectrum, then I don't have to worry about the negative parts of it. So if I do this, this is with a connective spectra.
So now, so there K was the non-connective, right?
So if you try to extend this to negative K groups, then you run into serious problems. One of the serious problems that you run into is that you would sort of like, what the heck is this? This is not defined for negative K groups. This, of course, should be 0 for negative K groups, I mean negative homotopy groups. And then this is probably non-zero in general for these things. So what the heck are you going to say? So when I'm talking about this, these are the connective spectra that you just get out of the Waldhausen.
But I'm saying there, K was the non-connective, right?
Yes. Let's do this to emphasize the fact that I have the non-connective spectra. And then I will also emphasize it by writing this is true for all n and z. Okay, now the next thing I want to do is repeat what I said in the garden last night. So there are more people in this room than there were people in the garden. So maybe half of you have heard this and maybe half of you haven't. So a differential graded ring is a chain complex plus it's a graded ring, and you have the Leibniz identity, which means that if I take the derivative of A and B, that's the derivative of A times B plus some sign times A times the derivative of B. I'm surely people in this room know what that is. Okay. So you can talk about a DG module. M, and this is a chain complex with a pairing M tensor A to M, satisfying the usual stuff. Now, the reason the chalk looks like it's getting really fat is because I'm at the end of that chalk. So there's a lot of things that you want to say when you say something is a module. And one of the things that what you want to do is write down a diagram saying M tensor A goes to M tensor A twice and goes to M. And another one you want to say is that the identity works right. And just write down the usual things. So this is what a differential graded module is. And the smallest subcategory of DG mod which contains A. So one of the things is that A is a differential graded module because of this Leibniz identity. So if you take a chain complex, you can shift it by a certain amount of degrees. The differentials change by plus or minus sign. And that's supposed to be allowed. And you also want to close it up under quasi-isomorphism. So if I have a map of two modules, and one of them's in my category, and the map is a quasi-isomorphism, then the other one should be in my category. And idempotent completion. So one way of thinking about this is that you want to sort of think of something as being a free module, which is a direct sum of copies of an alpha over some indexing set. So if you take a bunch of copies of A, you might shift them, then you would sort of think of that as being a free graded object, and that it can have summands, and those summands are going to be perfect. So this is sort of the generalization to differential graded algebras of the notion of perfect that I gave yesterday. And so then the definition of the K-theory of a differential graded is we take the K-theory of the category of these perfect A modules. And if A happens to be a differential graded algebra, which is all concentrated in degree 0, that makes it just an ordinary algebra in the sense that we teach undergraduates, then this is going to agree with the previous definition, because if you had just a classical ring, then the K-theory of A was the K-theory of perfect modules, as we saw before. So you can generalize this. From DG, well, let me say algebras, because that's the usual term that people use. If you are really sort of like anal retentive about this, then I mean algebras over the integers. So the algebra over the integers is a ring. But differential algebra is two DG categories. So Roman A goes to script A. And the point here is that the homomorphisms from A to A in category A, these are DG algebras. And the Hom ABs are chain complexes. Yep.
So this was your definition of perfect A modules, like the smallest subcategory of the modules.
Yes. 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 And if you don't have any kind of shifting going on, then you would just have a classical free module and a summand of a classical free module. Yes.
Do you need some other adjective in front of the subcategory? Like we should close it under sums or something? Or just this?
Yeah, of course I want to take sums.
Okay.
I didn't say that, did I? Thanks.
Is that all you need there?
I hope so. And I thought I had everything before, and I was wrong, so who knows?
Somehow the roughly is really roughly, right? So this is the analog of saying that.
Yes, this is roughly, because you could have, in principle, you could have something which is a summand of, right. So the finiteness obstruction that that Arthur was talking about yesterday in topology sort of has a kind of an analog here, that you might get that kind of strange behavior. So that's what the word roughly means. Okay, so then what is a DG module? M, well, it's a chain complex. So for every object A, you get a chain complex A, and it's natural in that. So that means that, so it's a functor from A into chain complexes. And you have M of B tensored with Hom of A, B goes to M of A. And then you want to have the usual compatibility. So I don't want to make a big treatise on this. I will tell you that if you look at Bernhard Keller, 2000, I hope it's 4, but it's probably 6. Bernhard Keller has a talk at the Proceedings of the International Congress about differential graded algebras categories, and he does a very good job of exposing this material.
I think there's a paper that goes with that.
Possibly. Oh, yes. So the point of part of this is that you can define the K-theory of this category to be the K-theory of perfect as before. And now the word roughly really matters, because now you have all of these different objects floating around. But what I wrote is it's the smallest subcategory of DG modules in this new sense, which are containing the representables, So what is that? That's B goes to, A goes to Hom AB. So these things are the analogs of the free modules. So you just plug in this sort of thing for that. You close it up under shifts. You close it up under quasi-isomorphisms. Thank you, Corey. You close it up under sums. And you close it up under idempotent completions, and you get a category, which we can call the perfect modules, and then you take the K-theory of that. This is a Waldhausen category. And so you take the Waldhausen K-theory of that. And then we have a definition for differential graded algebras. Eeps. Now you wonder why there's no long pieces of chalk. Okay, the other thing that I said last night in the garden was about the plus construction and the plus equals Q construction. So I don't want to spend a lot of time talking about the plus construction, but I need to say something, otherwise I'm not being fair. So if you have any topological space, you can look at its fundamental group. It's a group, and that group always has the largest perfect normal subgroup. And then you can form a new group, a space, which we'll call X plus, with the properties. If there's a map from X to X plus, 1 pi 1, it is pi 1 of x to pi 1 of x modulo e. So that's pi 1 of x plus. And The second property is for all coefficients A, the homology of x with coefficients in A to the homology of x plus with coefficients in A is an isomorphism. So the prototype of this is where you take x is equal to the classifying space of the general linear group of some ring. Pi 1 of x is the general linear group of the ring. E is the elementary matrices. And here is a theorem. Which is in the literature usually referred to as the plus equals q theorem. And that says that if I take the space k0 of A cross B, G, L of A with a plus sign, that's homotopic equivalent to the K-theory of A in the sense of Waldhausen or Quillen. Okay, that's my rapid run through of material that you may or may not have seen. So what happens if you have, there's a dot there. So suppose you have a simplicial ring. That means you have a sequence of rings and then you have all of these maps going back and forth, satisfying the simplicial identities. Then you can define a simplicial monoid. GL hat of A. So in degree P, GL hat of A sub P is the set of all elements G in matrices over AP with the property that under the map from AP to A0 to pi naught of A, the image of G is an element of the general linear group of pi naught of A. So if you have this map, then you get matrices over AP goes to matrices over pi naught of A. So this element that you started with a priori is just a matrix, but I want to say that that matrix is an element of the general linear group. So this is, roughly speaking, the homotopy equivalences of free A modules. So the idea is that instead of taking the general linear group, which are all of the linear equivalences, you're going to loosen it up and throw in some homotopy theory. So you can, since this is a monoid, you can form the classifying space of it, because you can take the classifying space of any monoid. Now you have a topological space. I can apply the plus construction. So I can put a plus on there. And the theorem is, so this is called the plus equals WS dot construction, that Kn of A dot is the same thing as pi n of B GL hat of A plus for n greater than or equal to 1. What happens with pi K0, you might ask? So by convention, Kn of A dot is equal to Kn of pi 0 of A if n is equal to 0, -1, -2, etc. So here's an idea of the proof. So here I was just talking about infinite matrices, but I could have put n by n matrices everywhere, and the entire definition would make perfectly good sense. So I can talk about GLN of A hat. If I take the disjoint union of these, this is like the disjoint union of the GLN of a classical ring. Let me use R to remind myself that this means classical ring. If you take the group completion of this category, then what you get is Z cross BGL of R plus. So this is, well, essentially Graham-Segal. So the group completion of a symmetric monoidal category is that you take loops B of your category. So this category has a natural monoid structure where you can just think about taking direct sums of free modules, and then you can take the diagonal of the matrices. So you can take B of this, then you can take the loop space of it, and Graham-Segal proved that that is going to be the same thing as this. And the same thing works here. The group completion is Z cross B GL hat of A plus. And now what you just check that this agrees with the other definition. So you just literally take this and you just look at it. And that's what Waldhausen did, and I'm not going to spend any more time on it, but I wanted to give you some sort of an idea about why that's true. So this is the WS dot construction of my category. Okay, so I think that I have successfully got myself to the point where I want to start doing new stuff once I find the okay. All right, so I'm going to just spend a few minutes talking about closed excision for rings. So what you can have is a diagram which looks like this. A goes to B. There's a surjection to a ring C, and then there's a surjection to ring D, and this is a pullback square. So if you think of this topologically, it basically says that you have two spaces represented by B and C, and they intersect in the space represented by D, and that A is represented by the space which is the union of these two things. So it's obtained by gluing the two pieces together along the common boundary. So what happens is if I is equal to the kernel of the map from A to C. This is isomorphic to the kernel of the map from B to D. So the ideals that are involved are exactly the same. And so we define the K-theory of A with respect to I. So this is the K-theory of A to the K-theory of A mod I, which I'll remind you is the ring C. And we have a natural map from here to the K-theory of B comma I, because that's the kernel of the map from B to here. And there's a compatible diagram like that, given by the functoriality of K-theory and this commutativity of this square. And so what you get is a fibration sequence of spectra, which, remember now, I'm allowing myself non-connective spectra, so just imagine that I've written double underlines under all of the Ks. So we have actually the following diagram, KAI, so these are spectra. So this is a sort of a commutative diagram of spectra. And in order to say that this diagram is homotopy Cartesian, it's the same thing as saying that these two things are homotopy equivalent, which is the same thing as saying that this is contractible, which is the same thing as saying that these two are homotopy equivalent. So we have several different interpretations of what it means for this square to be homotopy Cartesian. So this group right here is the obstruction to excision. So if it vanishes, if this vanishes, then these are, if it's contractible, these are homotopy equivalent, therefore this is a homotopy Cartesian square, therefore we get a long exact Mayer-Viator sequence. So the theorem, the first part is if n is equal to 0 or if n is negative, K0 of ABI is equal to 0 and K0 of AI is the same thing as K0 of BI. And K1 of A mod I, A comma I to K1 of B comma I is onto. And the same thing is true for negative groups. Kn of AI is isomorphic to Kn of Bi if n is negative. So this theorem grew out of the efforts of many, many people in the 1960s, and since that was 50 years ago, I'm not going to worry about the historical ins and outs of that. So this part is due to Swan, 1970. So K1 of A and B and I is isomorphic to. So this is the commutative case. A and B commutative. You can give a formulation in the non-commutative case, but it just gets ugly because of the fact that you have to worry about whether things are multiplying on the left or the right or whatever. So I mod I squared tensor over B mod I with the Kähler differentials of B mod I over A mod I. Now, because it looks nicer, you'll frequently see it written in this form. But if you do a little bit of algebra, you'll see that this is the same thing as this, and this is the way you would actually try to compute these things in practice. So the point is that there are cases where whatever group this is turns out to be non-zero. And what that means is that you can't extend the Meyer-Vietoris sequence beyond K1. To K2 to K1, that part of the Meyer-Vietoris sequence messes up. And the way that it's messed up is controlled by this group, which is the first homotopy group of this space. So one of the things that Morris-Kurtz is going to talk about is the fact that if you pass to schemes, that you get excision, but you don't get excision in exactly the same place. And in order to explain that, I have to talk about Zariski descent. Oh, thank you, Jim. Okay. So this is the section on Zariski descent. So for the sake of simplicity, we'll just imagine we have a base ring K, and we're just looking at varieties, but we can talk about schemes of finite type, essentially finite type, something like that. So what is a presheaf of spectra? That just means a contravariant functor. So if you have a map from X to Y, you get, let's call it E. You get E of Y goes to E of X. That's what contravariant means, of course, and that's all I'm saying. And of course, the main application that I'm thinking of is that the spectrum is going to be the spectrum associated to algebraic K-theory. Is there a question? Finite type. Yes. You can make further restrictions on it, but I don't want to be very technical. So the idea is that there's the global structure. And the global model structure goes like this. A weak equivalence is the same thing as for every x. So here is an E. So if I have a map from E to F, that is a weak equivalence, means that E of x to E of y, wait a second, F of x is a homotopy equivalent to the spectra. The cofibrations are the assertion that for every x, E of x to f of x is a cofibration of spectra. Roughly what that means is that spectrum is a sequence of objects, and term-wise you have inclusion cofibrations of the topological spaces, but then there's also an additional condition about the bonding maps that I'm not going to go into. And then the fibrations are determined by the right lifting property. Okay, there's also the local model structure. And because this is about Zariski, this is the Zariski local model structure. And the equivalence is to say that the maps from the homotopy groups of E to the homotopy groups of F. Well, now what do we have? That is something which is contravariant in X, and for every value of X, I get groups. And because of their spectrum, they're abelian groups. But they're pre-sheaf, so this is a pre-sheaf. But I'm trying to say something about the topology. And so I'm saying this is true for the associated sheaves. So the little tilde on that means to sheafify this pre-sheaf to get a sheaf. And an equivalent condition of this is to say that for every point X in X, so for every X, for every point in X, the homotopy groups of E restricted to X are isomorphic to the homotopy groups of F restricted to X. But then you have to sort of spend some time talking about what that exactly means, and I don't have the time to do that because I don't know if you noticed that I only get 1 hour and you get no questions. So I can't spend too much time on stuff like this. Okay. There's a model structure. And the same cofibrations as before. And the fibrations are slightly different. But they're again determined by the right lifting property in a model structure. So here's some notation. So this is the fibrant replacement. In this model structure category. So that's a blackboard bold H. And the point of this is that if X is Noetherian, finite dimensional, Noetherian, there exists a spectral sequence and I'm going to get my indices wrong if I think about it too carefully, but HP of X with coefficients in pi minus Q of E. So this means the associated sheaf of this. So this is a Zariski cohomology. and it's going to converge to the pi minus p minus q of h of x comma, well, let's not use that. So this is something that comes out of the woodwork, and it is originally due to Brown and Gersten, but it's been highly evolved since. Sorry, what? So it depends on how many details you want as to what you would consider a reference. A guy like you, I would recommend Thomas and Trobaugh. If you're more of a beginner, I would just say look in my K-book. I've got a discussion of this in my K-book, and I've got lots of references that you can look there. Sorry, Mark and I go back to the 1970s, so we give each other a hard time from time to time. And I leave it to you to decide whether he was giving me a hard time or I was giving him a hard time. Okay. So there's this main criterion. And that is that E is the same thing as H of blank E. Oh my gosh. So this is a global weak equivalence, i.e. for every x, E of x is weak homotopy equivalent to H of x comma E. So I want to remind you that the yoga that I'm doing, E is a presheaf of spectra, so E of x is a spectrum, an honest topological thing that topologists love. This is actually a spectrum as well, so here I have a map between two spectra, and to say this is a weak homotopy equivalence means it's an isomorphism on homotopy groups. If and only if for every covering of every space, E of x to E of u to E of v to E of u intersect v is homotopy Cartesian. So that's the criterion. But wait a second, I've seen that before. We had exactly that square for algebraic K-theory. So here's a corollary. There exists a spectral sequence where E2 PQ is equal to H P Zariski of x with coefficients in K minus Q, and it's converging off to pi, well, K minus P minus Q of x. So this is a pretty nice spectral sequence, and I'll illustrate it very quickly. Suppose you have a curve. So if I take the sheaf of K0, that's just equal to Z. And if I take the sheaf of K1, that's equal to the units. So since I'm doing the Zariski topology, I would write it like this. So here I would have H0 of x with coefficients in Z. Here I would have H1 of x with coefficients in Z. That would be nothing. Here I have H0 of x with coefficients in OX star. That's the units. Here I have H1 of x with coefficients in OX star. That's the Picard group. And of course here I have zeros. Because cohomology of a one-dimensional variety vanishes after H1. So here you have H0 of x coefficients in K2, blah, 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 H1 of x coefficients in K2. This line right there tells you that K0 of x is, well, H0 of xz. So this is z if x is connected, plus the Picard group. Because there's no differentials. So this is to sort of give you an idea of what the shape of the spectral sequence is. It lives in this quadrant. Well, it doesn't really, because it kind of leaks up here. But that would be negative K-theory, and I'm not talking about negative K-theory just for this purpose. But this is a descent spectral sequence. So here's an application. So suppose I have a square of varieties that look like this. Locally, so this is a finite map, and this is closed. Locally, this is exactly one of those A, B, I squares that I was looking at the beginning of the hour. So if I take the K-theory sheaf of this thing, then I'm looking at the homotopy groups of the double relative thing. That would be the K-theory. So this is locally K, A, B, I. So what does it look like? It looks like this. So the E2 terms are going to be the Zariski cohomology with coefficients in K minus Q. So here is Q equals to minus 1. Here is Q is equal to 0. These groups are all 0. This is H0 of K1 double relative, which I'm not going to worry about that. Here's HD on X, but it's actually a variety defined on Y. And here I have I mod I squared tensor with omega of y prime over y. And here I have zeros. And here I have stuff, which I don't really care about. The point is that this little thing in the corner has no differentials coming into it, no differentials coming out of it. And so what you end up getting is that, so what degree is it living in? It's 1 minus d. Well, actually, it's cohomology on y, because everything is supported on y. And this is the bottom non-zero excision group. And so what that means is you automatically have excision in all degrees below that. Now what you're going to learn when we come back from our coffee break is that in fact there's nothing below that. That's what Morris's big theorem says. one of the things that it says. But this sort of shows you that you can't improve on his theorem. And that's a good place to stop, so thanks.
Questions?
Yeah.
If you need further replacement with respect to which of
Oh, I'm sorry. So the 500 replacement is with respect to the local model structure.
this is where the Zariski topology.
That's where the Zariski topology comes in. And the point here is that if you plug in an Eilenberg-MacLane space associated with chain complex, so pretend that E is a chain complex, then this is the hypercohomology of the chain complex. Because how do you do that? You take a chain complex, you take an injective resolution, and the injective resolution turns out to be the fibrant thing. And so this would be the injective resolution, the cohomology, the homotopy groups of the space associated to it are the cohomology of the associated injective resolution, and so that's just the hypercohomology. So the reason for this notation is because in that particular case where this is coming from a chain complex, this is really hypercohomology in the sense of, you know, Grothendieck and EGA and all of those ancient things. Yeah.
About the K-theory of simplicial ring.
Yes?
What is K1?
There's a spectral sequence which tells you a little bit about K1, but in general, it's not easy to say what it is.
There's no simple description like the algebra. Because it is class construction. So
Well, you see, the problem that you have is that you have to understand what are the elements of the general linear group of A1, but not the general linear group of A1, the things in the GL hat sub 1 of A1. And that's where it gets a little bit messy and hard to describe what would be the input to K1. But there's a theorem that Goodwillie proved. Well, I don't know. Goodwillie proved that if you have a map of simplicial rings and pi 0 of A is equal to pi 0 of B, yeah, then the K-theory of A is isomorphic to the K-theory of B. And if the kernel of the map from pi 0 of A to pi 0 of B, where I is nilpotent, then you get a connection with cyclic homology. And I don't want to say more about it for several reasons, the least of which is that I'm run out of room. But the other reason is because it would open up a new conversation and we would never get any cake.
Does this mean this K-theory only depends on pi 0?
If this is true, yes. Am I getting his theorem right? No. So what? This is not right. I apologize. Let me try to spend 2 minutes fixing the record here. If pi 0 of A is isomorphic to pi 0 of B, then you get Kn of A to Kn of B, HC n minus 1 of A, well,
It's on the spectrum.
Hn n of A to Hn n of B, and that's a Meyer-Viator sequence. And so therefore the obstruction to these being the same is the same as the obstruction in what is essentially cyclic homology. Thank you for that correction, because that was just really stupid of me.
Is the K-theory principle of finite correspondence?
I'm not sure, I mean, the words are sort of like in the same circle of ideas, but I don't know that they go together like that. I don't know how to think about the K-theory of finite correspondences.
I mean, if there is a transfer, we have a...
So if you have a correspondence, a finite correspondence, so this is finite, then you want to sort of think about the K-theory of this situation. I think that's what you're asking.
There's a functorial map. If I have a finite correspondence from x to y, do we have a y with it?
Well, the point is that what do you want to do to reverse this? That's the trick. So you have a map from K-theory of x to K-theory of x tilde because it's contravariant. But then what you have to have is something going on here, and that's not so clear.
No, I mean, finite correspondence is active, not functorial. It's not compatible with composition of finite correspondence.
Yeah.
If x and y are smooth, then you have a map, but it's not functorial with respect to composition.
Okay.
So I would like to understand your very last application. So you gave a push-up diagram, right?
This one here?
No, the very last application. The diagram is a push-up diagram.
So I think
This one?
you changed your convention you learned from Swan. So
Oh,
you changed to our convention somehow. That's correct.
I'm not sure what.
No, that one's a push out, right?
So one of the fun things when you're dealing with spectra is that homotopy Cartesian and homotopy co-Cartesian are the same thing, right? So that's really a non-issue because I've got myself in a.
The scheme diagram.
Yeah. What about the scheme diagram?
finite growth.
That should be a push out because the associated thing I bring is a pullback, right?
Yes. So the point is that if I have A contained in B and this is a pullback, if I take spec, everything turns around and the pullback turns into a push out. So that's fine. Maybe I'm not understanding what the question is.
Because it's unused to have full push-outs of schemes.
So there's some work you have to do to figure out that actually makes sense, and it is a universal push-out. So push-outs of schemes in general don't exist, but as long as I put a finiteness condition on this, and this is a closed subvariety, then that's okay. But that's, yeah, I was sweeping that under the rug. There's a paper by Gillet in the Duke Math Journals around 1990 which deals with this issue.
So one question, this main criterion, does this also hold for other topologies?
For other?
Topologies in
Yes, this works for any Grothendieck topology. But you have to replace this condition by something else.
Okay.
So for example, for the Nisnevich topology, you have to add the elementary Nisnevich squares.
But what about Grothendieck topologies which are not generated by squares?
Then I don't know any great criterion. Just trying to keep it simple.
Okay, I think we should have some coffee now.
And cake. And cake.
And